So our final talk for the day on the main track is from Rajiv Shah, and it's going to be about quantum computing. Specifically, when will quantum computer be able to crack modern encryption, and what should we do about it? A question I think we all know the answer to, so please take it away, Rajiv, and welcome him to the stage.
Okay, all right, well, thank you very much. Thank you for making it to the end of the day and coming along to listen. So I'm going to talk to you about quantum computing and what we should do about it. Just my background came, I did a PhD in physics, and I worked for a company called Detica and BAE for about 20 years, and now, because I had one job for 20 years, I have about 6 separate jobs that I try and do at the same time. But I'll let you go and read my bio in the program. So what I'm going to talk to you today is take on a bit of a journey. So we'll talk a little bit about what is quantum, then we'll talk about what a quantum computer is, and then why do we care, and what should we do about it, and if we're going to do something about it, how do we actually get started? So why are we talking about this now? You're probably hearing a lot about quantum at the moment. One of the reasons you may be aware 2025 is the International Year of Quantum. It marks 100 years since some of the major developments in quantum theory, but also highlights the fact that there's a number of quantum technologies, such as quantum computing, that are coming to the fore. And although these might seem like quite long-term technologies that may take a while to get there, they're the sort of things where we need to start doing some work now to be ready to plan for the risks and the opportunities of those. So, what is quantum physics? Quantum physics is weird, right? That's the simple example. Quantum physics is not like anything you're used to in the real world. Because what quantum physics does is it explains how individual atoms and electrons and subatomic particles behave. And it's completely different from how things behave. You know, this is a solid lectern here. You know, I put my hand, it doesn't go through it. According to quantum theory, there's a probability I'm going to put my hand there and it's going to go all the way through. But that probability is so small, and therefore it never happens, and therefore that's what you expect to happen. But when we look at the details about how individual atoms and individual particles behave, it becomes very counterintuitive. And physicists like myself like to use like fancy terms like wave-particle duality, entanglement, and we've even brought in teleportation, because it makes us sound exciting, because you probably think we're going to talk about Star Trek, but I'm sorry to disappoint you, we won't talk about Star Trek. But as I say, it's complicated. So Richard Feynman was a famous physicist, and he said you can safely say no one understands quantum mechanics, which is why it's a really good subject to talk about, because then if anyone looks puzzled and doesn't understand what I'm saying, it means I'm doing a really good job. So. All right, what's quantum physics? Someone asked me, can we have a partial differential equation in there? So there's one, but don't worry, I'm not going to start trying to teach you differential equations at this time in the afternoon. What I will do, though, maybe examples, talk about an example called Schrodinger's cat. I don't know if people have heard about this. We've got any cat lovers in the audience? Okay, I apologise, this is entirely a thought experiment. As far as we're aware, no one's ever done this experiment. But Schrodinger's cat is one of the examples that Schrodinger came up with to just how weird quantum mechanics is. And it comes down to the fact that basically things are all probabilities. So say you have a radioactive source and it has a half-life of a minute. So after a minute, there's a 50% chance of it having decayed and a 50% chance of it not having decayed. And according to quantum mechanics, it actually remains in this combination of probabilities until you actually observe it. And when you observe it, it either decays or it hasn't decayed. And so if we now take this radioactive source, put it next to a bottle of poison, so when the radioactive source decays, it releases the poison, and then we put the cat in there as well, and we close the box up. As a thought experiment, don't worry, no cats were really harmed during the course of this. We close it all up, and then what happens, this cat is actually in this superposition of probabilities of being half alive and half dead, until we open the box up, and then we look and see whether it actually is or not. Everyone completely confused? Everyone think I'm talking rubbish? Again, anyone who's not shocked by it has not understood it, so that means I've explained it really well. Anyway, so the idea of this is really to help you to understand that quantum physics, as I say, is weird, right? It's not like anything you intuitively do and know in the real world. And therefore, that means sometimes you have to sort of suspend your intuition and your disbelief when we talk about what quantum mechanics can maybe do for us. And so, you know, we hear a lot about quantum computing, and yet when you think about it, all the computers we use today all actually depend on quantum physics. So things like LEDs and the fact they emit certain frequencies of lights, things like transistors and the band gap and the way that they work in switching electronic circuits is all because of quantum physics, right? All those different energy levels in there. And therefore, we actually use quantum devices all the time. So what is all this stuff that you hear about quantum now? The stuff we talk about quantum is sort of the next generation of quantum, or sometimes quantum 2.0, is where we're going to say, actually, instead of going from these sort of bulk quantum phenomena, we start getting to the point where we can manipulate and change the quantum state of individual atoms or individual particles. I was a theoretical physicist, and back in the days when I was doing my PhD, it was great, because we'd say, if in theory you could produce a single atom configuration, then you could do this, this, and this, right? And it was very safe to say this, because we knew no one had a chance of being able to do it. But now, you know, 20, 30 years on, people have worked out how to do it. Fortunately, those predictions that we made back then are proving to be fairly accurate. But what this means now is that we hear a range of different technologies, and some of the ones you might have heard is things like quantum timing, quantum positioning, quantum communication, quantum sensing. But obviously the one we're going to talk about most today is quantum computing. Okay, so what is a quantum computer? Well, it's a fundamental level. It contains something called qubits, and this is nothing to do with Harry Potter. I do apologise if you thought you were hearing a Harry Potter talk. But the physical qubits, they can be made in different types of ways. So we have things which involve superconducting junctions, some things which involve trapped ions, some that involve photons. There's a number of different sort of physical types of qubit that people are experimenting with and trying to use. And then on top of this, of course, that doesn't just make a computer. We've got to layer a few other things. So we need a control plane and some control circuitry, and assemble it all together into some hardware. And you see pictures like this. So this is a picture of an IBM quantum computer. You see it used a lot. It looks really pretty. It looks like a chandelier. The interesting thing about this, actually, is that if this pointer works, the actual quantum computer bit is just in there, right? It's a tiny bit in the middle. All the rest around it is actually cooling equipment, because these quantum computers are actually very delicate, and most quantum computers have to be cooled down to absolute zero. So, 99% of that is actually cooling rather than the computing unit itself. Then on top of this, we need to layer more. We're going to need some sort of compiler. We're going to need some sort of programming language. And now these exist. We have a thing called Qiskit, for example, that IBM has, which is a very simple scripting language. Anyone who's used a Jupyter notebook would be quite familiar with trying to use Qiskit. And then we need to run some algorithms on top of it. So that's sort of roughly what a quantum computer consists of. And why is it so special? Let's say quantum computers use this thing called qubits, right? And qubits are just very different from the standard binary computing that we do, right? When we do binary computing, you know that a bit is a 0 or a 1, right? And that's the two possible states that it can have. Qubits are different. Qubits actually have a continuous number of possible states that you can think of as points on the surface of a sphere. So what this means is a qubit can actually encode much more data, or much more complex data, than just a 0 or a 1. The other interesting thing about that is it also makes them much more susceptible to noise. Because if you think about it, with a binary computer, say you've got 0 is 0 volts and 1 is 5 volts, and the signal fluctuates and you get 4.5 volts, well, it's probably a 1 still, isn't it? Now imagine you've got a measurement on here and it moves slightly to there. Well, is that noise, or was that a genuine thing that happened? And therefore, that's one of these things that it makes a challenge in trying to get a quantum computer to work. But it also means, as I say, it gives you this amazing richness of complexity of the sort of things that you can encode and the sort of things you can compute, because you basically got so many more, basically got a continuum of possible states around the surface of that sphere instead of just a 0 or 1 in your single bit. And so what this means then is that we can also start to put these qubits together. And what it actually means is that these states on here actually turn out to be these probabilities. And if I put them together, you end up with combined probability distributions. And what this means is that the computing power scales exponentially with the number of qubits. So as I have more and more qubits, my computing power grows exponentially. And so what this means actually is that we can do something completely different from normal computers. And it's very important to remember, right? So you might hear people sort of say, well, quantum computers are just classical computers on steroids. And you say, people probably know better, say things like, well, a quantum computer will just do calculations faster, better, cheaper than a classical computer. And that's actually completely wrong, because people completely misunderstand it. If you want to do things like binary arithmetic, then you need to just stick to using standard classical bits and noughts and ones. But what these qubits allow us to do is actually do completely different types of computation. And therefore, what this means is you have things, for example, which are impossible to do or infeasible to do in a sensible amount of time with a classical computer. And we might find ways that with a quantum computer, we could actually run those and achieve managing those calculations. So what this really means is that things that we thought were computationally intractable now become things that we can think about doing. So rather than go into a lot of mathematical detail, again, I'll use an analogy here. And the analogy, stay with me on this one, is that giving someone a quantum computer is like giving a caveman a speedboat. And I'll explain a bit more, right? So imagine you were a caveman and what you had to do was climb up mountains to go and find food every day. If I come and give you a speedboat, it doesn't really help you get up the mountain. You could sort of do it, it'd be pretty difficult and probably much harder than just sort of climbing up there yourself. But once I give you a speedboat, it gives you the chance to do something you thought was completely impossible, which is, go across to the island on the other side of the river, which was otherwise just too far away and you were going to drown before you could get there. And therefore, this is the important thing I'd like you to sort of take away, is that with a quantum computer, it's not about trying to solve the problems we do with a computer today. It's actually finding those problems that we can't solve and finding imaginative ways of using a quantum computer to do them. And so obviously not all problems can be solved in that way, but there's a lot of active work that goes on into trying to develop these quantum algorithms where people say, well, if I had a good enough quantum computer, then this is an algorithm I could run on there and I could solve this problem that I know otherwise is impossible for me to try and calculate today using a standard computer, even using the biggest supercomputers that we have. And so people have found sort of three main classes of these problems that they can solve. The first one being these complex optimization problems, the so-called traveling salesman problem, where you're trying to find the best solution. An example, for example, is I think Transport for New South Wales is trying to use quantum algorithms to work out things like the optimum scheduling of buses and trains, those sort of big, complex, multivariable problems. The second class actually is around calculating quantum systems. This is what I did my PhD in, actually, was trying to do first principle simulations of things like chemical reactions and how a molecule binds to a catalyst. And if you can understand how that works, you can do things like design better drugs, design better materials, design more efficient batteries, and so on. And that's really difficult to do with a computer. Even though I was doing it 20, 30 years ago using a supercomputer, even with all the Moore's law advances since then, it's still very difficult to calculate realistic size systems. But it's likely that a quantum computer can often simulate these quantum processes much more efficiently. And the third one is this really esoteric thing, right, called factoring large numbers. Now, why would anyone ever want to do that? But this is an area that continues to be developing, people investigating potential algorithms. Okay, with this audience, I probably don't need to spend too much time, right? So we'll just briefly take a detour onto encryption. As you know, right, if you know to encrypt, you need a key, and so symmetric encryption, you need to agree a key with the other party in a way that no one else sees it. And, back in the analog days, we used to meet down a darkened alley or something, hand over a piece of paper, and that was the secret key used for communication. Now, when we communicate across networks, we need to find a way of agreeing a key that allows us to communicate securely with someone at the other end without anyone who has access to the network traffic in between being able to see that. And that comes down to public and private key cryptography. And at the end of the day, it rests on a very simple assumption. So it's a bit out of focus, I hope you can read that okay. That we can give everyone the public key, and it is impossible, in inverted commas, for someone to derive the private key from the public key. So as long as I keep the private key private, only I can decrypt the messages. Of course, when it comes down to it, that's not something that we can necessarily prove it's impossible, but we believe it's very difficult to do. And so we've come up with various encryption schemes, and if the cryptographers in the audience can bear with my simplification, at a simplest level, what we have is we have a private key which consists of two large prime numbers. We multiply them together, and the product of those is the public key. And that turns out to be one of these mathematical problems, which although it's an obvious simple calculation to do, it's very difficult to reverse. If you give someone the product and ask them to derive the original two numbers that we used to multiply it together, there aren't any efficient algorithms that anyone's found to do it. You basically just have to keep on guessing. And even though you might have been guessing, it doesn't even necessarily get you closer to the answer. You just keep on trying and trying and trying. And this is what fundamentally our encryption of data in transit relies upon, is this assumption of the assumed impossibility of being able to reverse that calculation. And it stood us in fairly good stead. If anyone's found a way of actually breaking it, they've kept it pretty quiet. And so we're reasonably confident that this is working for us. And this is therefore what we rely on every day. We have our padlock in our browser, our HTTPS or TLS. And it all comes down to relying on this factoring of prime numbers problem being impossible to reverse. A while ago, then, a man called Peter Shah then came up with a thing called Shah's algorithm. And what he said is, if you give me a big enough and a good enough quantum computer, I can actually do that reverse calculation. I can do that, solve that factoring problem. I can take this big number and I can work out what were the two prime numbers that we've multiplied together to get that answer. And so what it is, he showed, using various diagrams and how he could do this, that if you had a quantum computer that's sufficiently powerful, you could go and essentially do this. And obviously, this causes a concern, right? Because that assumption that we've all relied upon about it being computationally intractable to do that calculation suddenly may no longer be true. So I guess what's important to understand, though, is that what is vulnerable? So things like RSA encryption and also things that rely on discrete logarithm problems like elliptic curve cryptography, therefore, are potentially vulnerable to Shah's algorithm. What is not impacted is your symmetric ciphers. So things like AES and other symmetric ciphers are not impacted by this. There is a thing called Grover's algorithm, which people may have heard of, which people have hypothesized could be a way of trying to speed up, trying to break those symmetric ciphers. Essentially, it comes down to trying to do an unstructured search, but it doesn't give the same level of speed up. If you look at things like Shah's algorithm, it basically provides an exponential speed up compared to that brute force of trying to work out how to crack or how to factorize the number. Grover's algorithm gives you what I call a quadratic speed up. So it gives us a square root of the number of bits, factor of speed up. Now, the interesting thing, and you might want to think about this, so, we talk about these quantum computers and say, well, if we had a quantum computer, it could do this, right? But we don't have a quantum computer, and we don't even really know how fast it's going to run or how expensive it's going to be. So how do we even know it's worth it? And the reason often we know it's worth it is if we look at the scaling of the algorithm, even if, for example, the cost per step, we don't know what it is, if we have an algorithm which we know scales better on a quantum computer than on a classical computer, then we know for a big enough system, we'll be able to it'll be cheaper. But the thing about this is because it's a fairly small speed up, if you start to look at the details, it's actually quite difficult to run Grover's algorithm in practice because you can't parallelize it. It's very delicate, very susceptible to errors, and actually will cost you a lot just to sort of load data in and out. So it's probably unlikely. But if there was an issue, essentially with this sort of square root thing, if you double the key length, you still get back to that same thing. But to be honest, this is not really something we need to worry about at the moment. Okay, so I've told you what would happen if we had a good enough quantum computer. You've probably seen some headlines around in the last year or so. Google, for example, saying they've got this 100 qubit. Google's great advance in error correction, where they suddenly discovered error correction makes it better rather than making it worse, and that was a good big breakthrough. Microsoft announced this thing called the Majorana qubit with a roadmap to building 1 million of them. But if you go and look at the paper that they published and read the small print, they say, well, we may or may not have made one of them, but we're not entirely sure yet. And of course, if Google and Microsoft do something, then Amazon had to come out with a similar announcement fairly shortly afterwards. But possibly my favorite headline of the year is this one. Quantum computers making millions of these chips. So where are these millions of quantum computers? And if you go and read the small print, you know why they're building millions of them? Because they don't work. They make a batch of them. None of them work. They chuck them in the bin and they make another batch. And they've got up to 1 million or more already, right? And they haven't actually got them to work. So this is why you have to take the headlines with a bit of a pinch of salt. Perhaps a little bit more realistic is actually then what are people actually doing in terms of running practical algorithms on some hardware. And here we see people running things like that Grover's algorithm on 4 qubits. So at a much smaller scale. Of course, now you're going to ask me, so well, okay, if that's this, but what do we really need in order to get this, what point should we worry that our current cryptography is under threat? So what we have today is what we would call the NISQ, the noisy intermediate scale quantum computers. And by intermediate scale, we're getting to sort of 100, maybe people getting almost to 1,000 qubits in some of the hardware that they're building. But they're noisy hardware. Remember what I said about the fact that these quantum states are quite delicate because you can't easily detect noise in the way you can with a binary circuit. So they've actually become much more error prone. When you think about, you run millions and millions of steps of calculations on your computer and it always works. These things typically have about a 1 in 1,000 error rate, which, means most of the time you get the right answer, but it's still not that good. And that's why we call it the noisy stage. So what do we need to do if we want to break RSA 2048? So the latest estimates are that we would need 2,000 qubits, and you need about 10 to the 14 instruction cycles. 2,000 is maybe not that much more than that, so we almost got to 1,000 qubits. But that 10 to the 14 instruction cycles is the real killer. Because imagine that 10 to the -3 error rate. What's the chance of getting the wrong answer after 10 to the 14 cycles? Pretty certain it's going to be wrong. And what that means is if we're going to get the right answer, we've got to find some way of driving that error rate down to significantly less than that, many, many orders of magnitude less than what we're getting today. And generally the assumption is in order to do that, we're going to need some sort of error correction scheme where we have large numbers of physical qubits that we use into logical qubit, and essentially we try and detect and average out errors across there. And so what we actually get is about 1 million qubits as the assumption. And if you look at the sort of clock speeds you think we can achieve, that's going to take about 7 days. So that's 7 days runtime to run this algorithm once on a single public key in order to derive the private key. So is it doable? Is it significantly faster than doing it with current computers? Yes. Is it going to suddenly mean that anyone can instantaneously decrypt everyone's communications? Probably not. And the other interesting thing is you go and do the sums, is that's going to cost you about $250,000 of electricity, right? So once you get one of these quantum computers, right, and maybe you're given the task of going and decrypting some communication, you're probably going to think very carefully which session you're going to select to go and do the key. Because if you go to your boss and say, I spent $250,000 and I found a cat meme they were sending around the office, it might not be the best day in your career. Okay, so let's say what we've got to do is we've got to find a way of scaling up current quantum computers, right? So we've got these sort of small scale, noisy quantum computers, need to get the errors down, so things around trying to just suppress the errors, mitigation schemes where we may do calculations several times and try and average out the results, and then doing things like surface codes in order to correct the errors. And that's this thing where, we probably need around 1,000 of these physical qubits in order to get this one logical qubit, which has an acceptable error rate. Because bear in mind, we've got to get those error rates down to 10 to the -14 and currently on about 10 to the -3. And then beyond that, right, what we've got to do is at some point we're going to have to do networking and interconnection. Even if it's a short scale, we have a number of processing units and we need quantum interconnects between them. Most of these systems generally need to run at very low temperatures, so you're actually talking about large amounts of cooling. I showed you that picture of the IBM quantum computer and how much of the volume of that was actually the cooling equipment rather than the processing equipment. So as you scale that up to sort of 1,000 or tens of thousands of times that scale, the cooling becomes a real challenge as well. Of course, an interesting question is, are we even starting in the right place? Because we're all assuming, right, that the quantum computers that we have today are the equivalent of ENIAC. So ENIAC was probably the first modern computer back in about the 1940s, built using vacuum tubes. And obviously over years, we've got much better. They've become much smaller, faster, cheaper. But that was sort of the starting point. The interesting thing is, if you go back more than 100 years before ENIAC, and you'll know what this is? This is Charles Babbage's difference engine. So he actually came up and designed for this in the 1820s, has a subsequent version where he worked with Ada Lovelace on essentially what would have been the first programmable computer. Why did it never happen, and why was it 100 years later? Because essentially it was just completely the wrong form of physical form he was using, because this relied on using basically very carefully machined metal cogs, stainless steel cogs that sort of fitted together. And the problem was that actually you just couldn't machine it accurately enough, and you certainly couldn't scale it up enough. And so what we don't really know, I told you there's a number of different types of qubits that people are trying to build at the moment. Hopefully at least one of them is the equivalent of ENIAC, or even better, the equivalent of ENIAC was using vacuum tubes, and it's the equivalent of the transistor. But for all we know, it might be that we're starting off with technologies just fundamentally not going to get there because of engineering challenges. So, the question is, how long is it going to take? Well, we don't really know, but it's certainly, there's a lot of scientific and engineering advances that are going to be needed to go from those sort of current noisy quantum computers we have today to ones that will actually start to threaten things like modern-day encryption like RSA 2048. Of course, though, you probably heard some talk about harvest now and decrypt later. So again, you can think about this. So if I have a quantum computer in the future, if I now collect encrypted traffic being sent across the network, and I store it somewhere, maybe in 5, 10, 20 years' time when I have a quantum computer, I could then go and decrypt that data and look at it and find out what was in there. And you can see reasons why someone might do this, particularly if you're a well-resourced nation state. Obviously, you need to be able to collect all the data. You're going to be able to store it for a long time. But as I say, if you've got all this data stored and you've got your quantum computer, you're going to have to be very selective about what you start trying to decrypt in there, because it comes down to 1 week of runtime, $250,000 of electricity per key, right? So each session that's in there, you're going to have to go and spend that amount of money to go and decrypt it. So clearly the risk here is around if you have data that is, potentially of value to an adversary in the long term, and there is a good chance of them being able to identify from the metadata or however it's being collected that's likely to be of value, then this is a threat to worry about. But again, is this the sort of thing where, all our bulk messages are being collected and someone's going to suddenly be able to read them one day? I suspect we probably won't get there. So what does this mean? Does this mean the quantum apocalypse is coming? I've seen headlines from people, again, who ought to know better about things like Q-Day, which sort of suggests there's going to be one day someone's going to invent this quantum computer and suddenly all encryption will be broken and everyone can read all these messages. As I think you've now understood, that's not what's going to happen. It's going to be a much more gradual process. So there is no such thing as Q-Day. So again, please go and spread the message. That's my one-person campaign at the moment, is get rid of people talking about Q-Day. Again, you hear people saying things like, well, all encryption will be useless. And it's not all encryption, right? It's RSA, it's elliptic curve cryptography, things that basically depend on this factorization problem. It's not symmetric cryptography. That's not what's at risk. And as we'll talk about, there may be other forms of asymmetric cryptography which are safe. And then you hear people sort of talking about, what data do you have stored and how long do you need to store the data for, and maybe that affects your risk profile. And again, that really comes from misunderstanding, because again, you're not worried about the security of stored data, right? When we encrypt data at rest, we typically use symmetric encryption to encrypt data at rest. And so what data you have stored or how long you store it for is completely irrelevant. What's important, or what you might want to be worried about, is where you have data that you send across a network, where someone might be able to read the data on the network, and that data has value to someone else in the future. It's not to do with how long you store it for, how long is it of value to them, or at what point could it still do harm to you if that data is seen. So important things to think about: what is the threat is data in transit and data with long-term potential for harm. The other thing actually is around authentication. So I've talked a lot about encryption, but these same processes are used for digital signatures, and therefore things like authentication, and particularly signatures that we may put out there, certificates we may put there for long-term root of trust, for example, things like hardware and firmware upgrades. Again, those are the things that we may want to be concerned about long-term risks for. So what does it mean? As I say, it's not going to be Q-Day, it's not going to be the apocalypse, it's more like the boiling frog. Because at the moment, we all have this assumption, as I said, right, that RSA encryption or whatever is safe because no one can derive the private key from the public key. And over time, we'll probably be less and less certain of that assumption. And therefore, those highest risk cases, we'd be most worried that someone might be spending some money and going and actually breaking that assumption. So we're going to have to do something about it. Now, what should we do? Okay, so these quantum physicists have come up with these wonderful quantum computers and now cause us this sort of security headache. Is there some quantum technologies that can help us? And you may have heard some of these discussed. One is quantum random number generators. Again, this is a cool piece of physics. It comes back to those probability distributions and the fact you don't know whether something's actually 0 or 1 or whatever until you measure it. And so the idea is that you can use the properties of quantum mechanics to do genuinely random numbers, not on this pseudo-random number generator or things like thermal noise random number generator that we use at the moment. And so maybe from a cryptographic point of view, it sounds like a brilliant idea. And it is 100% guaranteed randomness we can get. It's also 100% guaranteed useless against this quantum threat from the Shah's algorithm. Because Shah's algorithm doesn't rely on anything about weak entropy or the pattern of the key generation. No matter how perfectly your public and private key pair were created, Shah's algorithm means you can reverse from the public key to the private key. So this isn't going to help us. Another piece of cool physics, right, that you may hear people talk about is quantum key distribution. And this actually relies on that thing around the Schrodinger's cat. The idea is that once you open something, it stops being in a quantum state. So that you can reverse this and say, actually, I can now put something in a quantum state and I can send it across to you at the back of the room. And if you open it up and it's still in a quantum state when you open it up, until you open it up, then we know that no one has looked at it in between. Now, if someone in between intercepts that box and opens it up, then it collapses out of that quantum state. And we know they've seen it. So this potentially gives us a way of creating a shared secret between us, right? With 100% guaranteed certainty, theoretically, that no one has seen it. And so this is called quantum key distribution. And you may have seen headlines like this. And again, with an audience like this, it's probably red rag to a bull. Anyone believes anything is hacker-proof? No, I didn't think so. And so some examples about how you could do this. Because I say, right, from a theoretical point of view, this channel here is 100% guaranteed secure, as in I can know for certain if someone has seen the data en route before the data gets from Alice to Bob. So what are we going to do? If you wanted to hack this, where would you start? Well, the first thing you've got to learn, this diagram's only partially there, because what happens is we have this key, for example, that gets sent across, but Bob needs some way of telling Alice that which bits of the key is received, which he knows no one has seen in between, and whether it's got through. So what this means, actually, if you look at it, is you need a classical authenticated channel as well. So you have this quantum channel, right, between here and here, 100% guaranteed secure. So what could we do? Well, the first thing actually you could do is a simple denial of service attack. If your threat model is that Eve has access to all the data on the network that is sent in between the two endpoints, then what could you do? You could just sit there and you could just read all the data. And every time Bob says, oh no, someone's already looked at it, send it again, send it again, send it again, the message never gets through. So denial of service attack is pretty trivial to do on this. The other thing, obviously, I sort of showed you that classical authenticated channel. Well, maybe we can't hack this link, but we may be able to find vulnerabilities in this classical channel. And what's another thing you do? Oh, you're probably all ahead of me on this, right? Is obviously you could go after the endpoints. And it turns out, as I say, the words in theory do a lot of heavy lifting in talking about quantum key distribution, because these endpoints are actually quite difficult, because you've got to get these things that can send out single quantum states, single photons, one at a time. And therefore, the things you can do around the characteristics of those endpoints. And also, generally, it's just very difficult to do reliably. You can get this working over about 100 kilometers of fiber. Again, if you go back to that headline I showed you, it talks about sort of 900 kilometers or something. That's done by a satellite. Waiting until night time, waiting until clear skies, and direct line of sight from the ground station to the satellite. So it's actually very difficult to do. So again, this sounds like one of those really cool pieces of physics. It's like quantum random number generators, quantum key distribution. I'm a quantum physicist. They're cool pieces of physics, and they're really exciting. But practically, they're no use. And some guidance, actually, that even ACSC produced just at the start of this week makes it very clear that it's not seen as a secure form. The UK NCSC did some advice about a month ago, which was even more explicit. I think it said, if you try and use quantum key distribution, we don't see this as basically satisfying your obligations to secure your data. So what are we going to do? We've got to go back to the mathematicians. The same mathematicians that gave us the wonderful RSA and elliptic curve cryptography I've got to find some other solution. And what we need to do is find some mathematical function that allows us to do that private key to public key mapping, but makes it almost impossible for someone to reverse the calculation. So we're going to find some new maths, new asymmetric algorithms. And these end up being generally called post-quantum cryptography. Sometimes people get picky and say, well, it's not post-quantum because we haven't got a quantum yet, so we should call it quantum-resistant cryptography. Again, in my attempt to clean up terminology, if anyone says quantum cryptography, please correct them, because it's not quantum cryptography. Because in actual fact, this is just about new maths that we can run on today's computers, right? It's not about the fact that we need any of this fancy-schmancy quantum hardware or quantum systems to do it. So it's not quantum cryptography, it's post-quantum cryptography. And so how do we find this new form of maths? Well, fortunately, we have been thinking about this for a number of years. So for about 10 years, NIST has been running a process where they basically issued an open call for proposals. People put forward ideas. And a lot of these sort of mathematical ideas have been out there for a long time. You know, we end up doing things like the elliptic curve and the RSA cryptography because they were quite easy to implement. So people have dusted these off. People have tried them out. Of course, some of them didn't work. You know, people came up with these quantum-safe algorithms, and then, you know, people were going to try to crack them and found they could. But the good thing, right, is it's taken about 10 years. So hopefully all the stuff that has now survived all this process, people have had a good go at trying to break it. And we have a good degree of confidence that it should be okay. And so what we have is these things called lattice cryptography is what's been used. And so at the end of last year, NIST published 3 standards. So I've sort of highlighted on here. This is the recommended strength, for example, in the ISM for key encapsulation. Interesting, I don't know how well you can read that, right? But one of the things that we do see, and it comes back to why do we end up choosing, even though this sort of maths was known about 50, 60 years ago, the reason why we did RSA was it was actually quite efficient, right? So RSA is 256-byte key size, 256-byte cipher size. The sort of sizes we get here are 2, 3, 4 times that size. So it is going to be less efficient. When we look at the signatures, so the sort of general replacement for elliptic curve digital signature algorithm, is actually even bigger. So we're seeing probably almost 10 times that. And there are actually people that are concerned that this particular signature method is not as secure as we might want it to be. So sort of extra secure hash-based one. And if you look at the numbers there, you can start seeing we get some really large signature sizes. So, you know, there were good reasons why we didn't try this when we didn't need to, but now we know what we're using is susceptible to a future quantum computer. We need to find new things, but we need to realize it's going to introduce extra overheads. This debate is sort of still going on, and again, it probably comes back to, so if you go back to the 1990s, right, in the history of the internet, right, back in those days, a group of engineers, mainly in the US, came up with a whole load of standards, and geopolitics was much simpler, and everyone just accepted them, right? And we can say that as a result, we probably missed out a lot of security in the current internet, right? But we can have that discussion another time. But what happens here is that NIST has gone through this process. Even though it's been an open, transparent process, anyone around the world could go and contribute proposals, anyone around the world could examine these proposals and try and find vulnerabilities in them. Not necessarily everyone trusts the Americans in the way they used to. So the EU, for example, is saying, well, maybe these things are not quite secure enough. We've got another algorithm we think we should be using. Probably to no one's surprise, China doesn't necessarily trust the US's algorithm, so China's talking about developing its own algorithm. So this is definitely still an evolving area. And again, maybe it comes down to this problem. At the end of the day, we can't actually prove, right, that RSA is secure, right? We just hope. Because if anyone's found a way of breaking it, they've kept very quiet about it. But we think it is. So again, now we've come up with these new algorithms, and potentially, and as you saw from an example of one of the ones that have been tried, you know, we might have these new algorithms we think are safe from a quantum computer, but we end up introducing a vulnerability that means that a classical computer can break it. So in trying to protect against that threat in the future, we might make something insecure now. And so therefore, what we have to be ready for is that we've got these standards, we've got some ideas about what we want to do, but this may not be a one-off change to cryptographic algorithms. So as we upgrade systems, we need to make sure what we call crypto-agile, so we're able to make future upgrades if we need to. And depending on your level of paranoia, one of the things that people often talk about doing is actually sort of encrypting data twice. So encrypt it once with RSA, and then encrypt it again with the post-quantum cryptography. So if the post-quantum cryptography, for example, turns out to be susceptible to a classical computer attack, your data is still safe because it's in this sort of double-wrapped or double-encrypted state. So we sort of worked out what we need to do, and we sort of probably need to get on with it. Because although it sounds relatively straightforward, all we've got to do is run some different algorithms on the same hardware. It's just a software problem that's going to write some new stuff. It's obviously going to be a big, complicated ICT project. And one of the biggest problems actually is going to require multi-party agreement, right? Because you can upgrade all your systems, but unless the person that you're communicating with upgrades all their systems in a compatible way, and coming back to that potential fragmentation of standards I've alluded to, That could be a challenge. And the other thing is that, we've been using the current systems for a long time, right? And we've got the standards written down, but how much sort of law and practice is built around that, unspoken assumptions and how we've implemented it, that when we go and try and change the implementation, we maybe break those assumptions. I'll say the other thing is going to be there is going to be additional overheads. There are additional sizes around that key and signature, which can add communication overhead. There has been some concern that also these things are probably some extra processing load, although some of the benchmarking that NIST has done suggests that's not that significant. It may be a sort of 10 to 20% extra CPU load for what's been standardized on. But again, it comes back, why did we use the current algorithms? Because they were actually quite efficient and cheap and easy to implement. So we'll have to be some compromises. And then the other thing is going to be complexity, right? These algorithms are more complex. We're less familiar with them. We just don't have the experience, right? And again, what is complexity? Complexity is the enemy of security. So once we start to introduce this, there's the risk that as we make these upgrades, we're going to introduce vulnerabilities. And because we don't have that same experience of working with, we don't have as many trusted libraries, for example, that we can use. So we need to be wary of that as well. Okay, so I was going to talk about some experiences, right? Anyone got an iPhone? Those of you with an iPhone, iMessage was upgraded to post-quantum cryptography over a year ago, probably about 18 months ago now. Did you notice? You didn't notice. It just happened overnight. One day you woke up. And obviously this shows how easy it's going to be, right? You hit me. Yeah, obviously it was easy for Apple because they own the whole ecosystem, right? They own the device, they own the operating system, they own the endpoint software, they own all the servers in between. And therefore it's actually a relatively straightforward and seamless upgrade for them to do. A few things about how they did it. They used this double encryption, so they did have this sort of paranoia. They said, we're not just going to rely on post-quantum, we're going to encrypt everything twice. And at the moment, what they've done is they've just actually updated the content. What they haven't done is upgraded their authentication. And the reason for that is that content is something which is subject to this harvest now and decrypt later, whereas authentication is not something you can go and exploit in the future. Or if someone can go and exploit by replaying your authentication in 10 years' time, you've got bigger security problems to solve. So obviously, Apple did this update. So, Google said, well, anything you can do, we can do better, right? So a couple of months later, they decided to upgrade Chrome and released an upgraded version of TLS in Chrome that would support post-quantum cryptography. How do you think it went? They broke the internet. Not quite, right? But it just didn't work. It broke everything. And why did it break? And the interesting thing about why it broke comes down to these unspoken assumptions. Because what happened was because they had these larger packet sizes, some of the routers in between looked at these packet sizes and it's like, they said, that's weird, that's unusual, that's not what we expect. That is abnormal network traffic, something funny is going on, I'm going to drop that packet because there must be something wrong in it, right? Even though it was within the standards, it was outside of normal behavior. We just had this unspoken assumption, no one would ever do that. Who would ever do that? If someone's doing it, either something's gone wrong or someone's trying to do something dodgy, so I'm just going to drop it. And then it turned out also various things about fallback negotiation methods also didn't work, and therefore what happened was the connections were getting dropped. So they had to roll the change back. So what do we learn from this, right? Is that there's, from these years of implementations, all this sort of folklore and practice, we're going to have to unwork. When we do it, as I say, it was easy for Apple because they own the whole chain, so they could very easily, test everything end to end. As we do upgrades of individual systems, you're going to do a lot of testing with all the potential counterparties and make sure that testing tests all those different corner cases of the protocol, all the weird things that, doesn't normally happen, but maybe the standards allow to happen. We need to make sure we test those. Quick, a couple of other updates. So AWS, for example, then started doing this. They've started providing support at the end of last year. Interesting, there's also their default to that, which suggests that they don't expect, again, a massive performance hit from it. And the other one I put up here is Microsoft, because obviously so much works on Microsoft. So Microsoft has recently released a roadmap around how they're going to do this. Probably the important thing to note is it's end of 2029 when the main sort of things like Windows services, Azure services, endpoint, Office 365 will be quantum safe. So that's the sort of commercial roadmaps that we're seeing. So what do we need to do? Some of you may be aware there's been a few updates from the government recently. So the ISM was updated a couple of weeks ago and came up with a couple of things. So one's actually been there for a while, which is basically saying we recommend support for these new algorithms no later than 2030, and also a requirement that organisations should develop and implement a migration plan for implementing post-quantum cryptography across their environment. Monday this week, which made me have to go and rewrite my slides, there was some further update that came and actually proposed this. And again, coming back to, we sort of talked about when is this likely to happen? The most optimistic, pessimistic on your point of view of how we might get to a quantum computer that can break RSA 2048 is probably about 5 years away. More pessimistic is probably 15 years, maybe even longer than that. And so what they've said here is, sort of less likely 2030, more likely 2040. Come up with then some quite, let's call them ambitious targets. That by 2026, that's next year, fortunately the end of next year, you should have an implementation plan, start implementation by the end of 2028, and by the end of 2030, recommending that actually all migration should be completed. This is quite an ambitious schedule, and it's probably more ambitious, for example, than most of our partners are done. So the UK, for example, has a very different one. Although, the UK said the start of 2031, we're saying the end of 2030. The UK said what you need to do is upgrade those high-risk systems. So coming back to what I said, those sort of things where you'd be worried about those harvest now, decrypt later, or sort of things where you've got this long-lived certificates, root of trust that you're putting out there. Those are things you need to focus on as high risk, and then the rest can be done by 2035. So we'll see where this goes. As I say, this is hot off the press. This was literally Monday morning this week, this guidance was published. But what is in there, and what I'll expand upon, is actually a really good framework. So we talked about, how are you going to get started? And the first step in actually doing this is making sure you understand where cryptography is used across your organization. And you could argue that regardless of the quantum threat, actually having a better understanding of where cryptography is used, what cryptography is used, and what data it is protecting is good cybersecurity practice. And then having done that, then assess each case and look at, which ones are vulnerable. So again, coming out to if it's symmetric encryption, don't really worry about it. If it's using asymmetric encryption, is it using one of those vulnerable algorithms? If so, then, what do we need to do? How easy is it going to be to upgrade? And the first thing probably is to go and talk to your vendor. And as I say, 95% of your cases, you'll be using something like Apple or Google or whatever. Go and talk to the vendor, check their roadmap, make sure they've got a plan for upgrading it. Then the most important point is triaging, because as I say, it's nice that there's a target out there to try and do all of this by 2030. There's always going to be a tail of things that don't get done. So what you need to do is work out which is the highest risk systems you want and make sure you prioritize those. And so the sort of things that make you prioritize it, is if you've got data that has long-term value, if it's going across public networks where it'd be easy for an adversary to collect the ciphertext. If you've got systems are going to be difficult/impossible to upgrade, so those upgrade paths might involve, ripping out some physical systems or going around a large number of sites around the country, those are the ones you need to start early. Otherwise, if you've got things like interoperability, again, these are all things where you want to start early. Really, things where you might want to just wait, right, is the vendor roadmap, right? I'll tell you, Microsoft's got a roadmap that says they'll upgrade things like Office 365 by 2029. Probably the last thing you want to do is start layering in some extra encryption system on top of your Office 365 now in order to try and get out of that. You just want to wait for that roadmap to come through, because again, start putting more in, more complexity, more opportunity for vulnerability, more opportunity to get it wrong. And the other thing you might think about, what are natural refresh cycles, and also maybe where do you have additional protections in place? If the data is not traveling across a public network, maybe the risk of someone sitting there and collecting that encrypted data is low. And if it's on your internal network, well, if an attacker on your internal network, maybe you've got a different threat to worry about. So these are sort of things you need to think about. And this is actually the most important section, is about how do you triage. Having triaged it, then you need to think about how you implement it. Good ways of implementing, hopefully, best case, the vendor's still around, the vendor still supports the system and apply their patch. I always imagine things like go and upgrade libraries or go and procure new systems. Things to avoid, if you can at all do it, is handcrafted code, because generally roll your own crypto, not advised. Non-standardized implementations are things to be wary of. And these are the things you need to think about in coming up with your migration plan. And so you may have noticed the sort of acronym, so we sort of locate, access, triage, implement, and alongside that is communicate and educate, which comes to lattice. And you're told is lattice-based cryptography. You see what they did there? Okay. Who says the government doesn't have a sense of humour? Of course, they got the spelling slightly wrong, so I came up with my own tweak now, which actually says that because triage is the most important point, maybe we should triage twice, and then I can get the acronym right? And now I can claim credit for it instead of giving them credit for it. All right. So that brings us really towards the end. The closing thought I give you is say a lot of this quantum stuff sounds very fancy. There's a lot of hype out there in the market. I showed you some of the headlines and things that are out there. But what will happen is I think it's one of those typical technologies where we're overestimating in the short term maybe what it's going to do. There's going to be some disappointment that's going to come out in the next few years. I was on a meeting this morning where people talk about, people are just sort of quantum washing everything. You say something is a quantum thing because then it sort of gets you funding, gets people excited and so on. But in the long run, we're probably underestimating some of the fundamental changes because things like quantum computers mean there's a lot of things, not just things like code breaking, which are just impossible for us to do with computers today. Even we scale up our current supercomputers, suddenly they become computationally feasible problems for us to solve. So if we just summarise, So as I say, quantum computing, the important thing about quantum computing is it will undermine the commonly used methods for encryption of data in transit. It's going to be a gradual process. It's not suddenly one day everyone is going to have instantaneous access to decrypt all the communications. We'll start off with, very big, very expensive things, and they'll be used for the highest value targets. Over time, we probably expect, a bit like Moore's law now, things will get cheaper and easier to use, and the threat will become more widespread. So it doesn't mean there's no need to panic, right? So don't panic, don't go back and say, right, we need to upgrade everything tomorrow. But what we really need to do is we do need to start now planning, because we know that some things are going to take us a long time to upgrade. Next one, this is not a quantum technology, unless it helps you get funding. If it helps you get funding, go and tell your boss, yes, I'm building a quantum network, right? But otherwise, please be very careful with your terminology, right? Because it doesn't require any of this fancy quantum stuff, right? The quantum physicists can keep developing their quantum hardware and their quantum optical systems and their qubits and all of that. You don't need to wait for any of that. This post-quantum cryptography is something you can start to roll out now. Obviously, you will have challenges in some cases where you've got things like embedded hardware, you've got HSMs, you might need some hardware, but it's not about a whole new generation or completely different type of hardware. So it's one we can get on and start implementing now. And then what you're going to find, I'm guessing here, right, is that as you do that, locating everything and assessing everything, you discover that 95% is probably pretty easy for you to upgrade, right? Because you're just going to apply the patch to Chrome, apply the patch to Office 365, etc. And it's going to fix your problems. And that's probably the problem is that's probably the low risk stuff. The stuff that's going to be really difficult, the last 5%, is probably also the stuff that is highest on that triage. So come back to that triage, it's the high risk stuff. So you might see a target, someone might tell you need to do everything by 2030. If you can only do some of it, don't chase a metric around what percentage of your systems you've upgraded. Make sure that you prioritize by the highest risk, right? So let's make sure that 5% that's going to be very hard, but it's going to be the highest risk. I know it might be a bit of disappointment, to go after the most difficult one first. Again, it's not a good thing to report to your boss, but that's where we need to be concentrating our effort on. So that's everything. Thank you very much. I'm very happy to take questions, comments.
Thanks, Rajiv. Do we have any questions?
Thanks, mate. That was really interesting. A little bit off topic, but do you have anything to say about what the killer app might be?
Oh, I still mic'd up on it. Okay. It's late in the day, sorry. I don't know, and it's a very good question, right? It's one of these things where, we're sort of building it and they will come. It's a bit like 5G, to be honest. We rolled out 5G, have we found the killer app yet? My personal feeling is that, and maybe it comes from my bias of a background of having done this sort of quantum chemistry stuff, is I think the opportunity is actually to do things like speeding up those quantum mechanical first principles calculations. They are fundamentally just really, really difficult to do on a classical computer and really, really difficult to scale. But if we can solve that, the potential for sort of like the value that we can deliver there through things like as designing new drugs, providing new materials, more efficient batteries, there's actually a huge number of opportunities there, where at the moment we're mainly constrained by the fact that you have to go and synthesize things in a lab and then test them. Even if you can't get perfect answers, if you could go and use a quantum computer, for example, to whittle down to a short list of a dozen things that you then need to go and actually fabricate and test in a lab, there's potential there to speed up those development cycles massively. So that's my personal feeling about where I think the killer app might be. But we really don't know. And again, probably an area that's underexplored, I think, is actually people trying to just think about these problems. What are those problems which we can't solve with a computer today? Can we find a quantum algorithm that means that we're ready when the quantum computer comes along? And that could take us several years to do. So we'll see.
Thanks.
Got a question down here. Then.
So firstly, fantastic talk. And my question is, who do you think will win the arms race? China or America, or maybe even another company like Europe?
That's a really good question. And one of the things I talked about, actually, there are people trying to build qubits with fundamentally different physical building blocks, right? Some people are trying to use photons, some people are trying to use neutral atoms, some people are trying to use ions, some people are using superconducting junctions. And sometimes people come and ask me and say, well, which technology is going to win? And I tell them if I knew the answer to that, I would have invested all my money in the winner and I'd be offered it out somewhere else. So it's very difficult to know. I think in terms of where we are generally, the US is probably the leader. But there are some very strong capabilities in Europe. Australia, actually, some very strong companies like Silicon Quantum Computing and Dirac that both came out in Sydney, are very strong in this area. And it is one of those things where we don't know, right? Who is building ENIAC and who is building the Charles Babbage difference engine? It's very difficult to know, because some of these things people will only find the fundamental scaling limit with their technology maybe in several years' time. So it's really difficult to know. Balance of probabilities, from what we can see today, and you've got to bear in mind probably that the West is much better at openly publishing where it's at. But if you look at openly published literature and progress, West is ahead, the US is ahead, the UK is strong, Australia is strong. Germany actually has got some very strong quantum companies as well, doing quantum hardware. But there's always it's very early in the race. There's a good chance that one or more horses is going to stumble and fall. So we don't know who's going to win.
I've just got a question up there first, and then.
Thank you. Good talk. Thank you for that. To the question of what the killer app is, now this is a bit left field, but I understand that that in the old days of the Bitcoin protocol, it was common to pay to a public key, and the public key would become public. And I don't know, but I imagine there might be addresses in Bitcoin that have, I don't know, maybe 10,000 Bitcoin that might be worth, I don't know, $1 billion. I've been wondering if perhaps the killer app is just cracking those old Bitcoin addresses. And I've also been wondering if we might know that we've reached, if you'll forgive me, Q day.
No.
The day suddenly a whole flight of old Bitcoin addresses start being drained. I don't know, but I'm just interested in your thoughts about whether or not that might be a thing.
Yeah, it's a really good point. And $250,000 worth of electricity to recover a single private key, depending on motivation, that might be one of the places you'd start, right? Is actually going and doing that. And another good question, people say, well, will we even know when this happens, right? And I go back to the story of the Enigma being cracked, right, in the Second World War, right? Once the Allies knew how to decode those messages, they had to be very careful about how they acted on what the information they decrypted, because they wanted to give away the fact that they had the ability to decrypt. And so you can imagine the same thing happening when someone can come and break this. But, maybe at the end of the day, temptation will come in. If the right person with the right financial motivation gets access to it, one of the first things they might do is go after that. Well, and that would be a very obvious sign, right?
I think the way Bitcoin works is it's a race. Like, it's all of us, like if you can get in first, do it now. Like, don't wait. Because
go and build a quantum computer. And we'll have a hardware village in BSides.
So it seems like a pretty, if true, it seems like a pretty reliable way to know that, that it's possible, because if there are people who can do it who aren't doing it, I mean, it just doesn't seem pragmatic.
Yeah, although you've got to remember, given the resources needed, chances are it will be a nation state, probably, or an agency that has this capability first. It's probably beyond the means of the criminals. Now, there are certain nation states, for example, North Korea, we seem very financially motivated in its cyber activities, so maybe if they got there first, but we had the question, I haven't said anything about them. They don't publish anything about their research. But you're right. But again, if you had it, you might be very selective how you use it, because it's one of those things you burn once, right? And then people will very rapidly go to change that.
We've got one down the front.
What makes an algorithm, a quantum resistant encryption algorithm, resistant to quantum computing? Is it just the fact that it doesn't depend on factorizing, working out the factors of a
yeah, I mean,
why is factoring so like just the only kind of thing which makes an algorithm susceptible to quantum?
So the first simple answer that comes out to the fact, actually, we don't know, right? So we've come up with these new algorithms and we have hypothesized that they are quantum safe, right? And we can't ever prove that hypothesis. Someone could disprove that hypothesis by finding an attack against us. People have found classical attacks against them. And there are people trying to look and see, because so I'm trying to think how to get into a huge amount of detail. But so the reason why factoring works is one of these things about the fact that quantum computers can do these different types of calculations. And there's a thing you can do which basically involves working out sort of periodicity. If you imagine sort of having a wave that goes across a pond, right? And there's a way of doing a quantum calculation, the wavelength that gives you an exact number of peaks and troughs, an integer number in that pond, right? And that's essentially the factorization problem. So what's happened is someone has found an algorithm to reverse the factorization issue, right? All I can tell you for certain now is so far no one has revealed that they have an algorithm that they can run on a quantum computer that can reverse lattice cryptography. But that's actually all I can promise you now. And there was an interesting thing. There was a paper that was published earlier on this year by a Chinese researcher where he actually claimed that he'd found a quantum algorithm that allowed you to reverse this lattice cryptography. And it caused a huge amount of activities you can expect amongst the community. People went and sort of reviewed in huge details, and eventually they found sort of a fundamental flaw. And you've got to remember, people are coming up with these algorithms, right? They have to do them all on paper. The hardware doesn't even exist to test them now, right? So people are coming up with these, and then other people go and review your work, right? And maybe found an issue there. But it's a very good question. That's why it comes back to this point. I say we have to be aware that as we do these upgrades to encryption, that it may not be the last one we do. So as we go and upgrade systems, we need to think about how do we make them crypto agile in a way that if we need to go and do another upgrade, because we do discover that these algorithms are quantum susceptible, and we have to change to something else completely different in a few years' time. Hopefully, we've done a fair amount of the groundwork that allows us to do that.
Thank you.
We might have time for one more. Oh, there's two more. We'll just go the one here. And then one at the back after, and that will be it.
Rajiv, do you think that, given what we've just spoken about, that information theory might have something to provide in terms of something on the other side of post-quantum cryptography? Do you think that's a...
So I think the question is, could I use
solution
information theory to prove that something is quantum safe?
Correct.
I think the answer is no, because no one's actually found an information theoretical way of proving that RSA is safe, right? The information theoretical secure ways, there's two things. One is around, a one-time pad, but that involves some way of then securely sharing that one-time pad, which we're back to the old problem. The way that is information theoretically secure is quantum key distribution, in theory. And then, this comes back to, right, again, everyone in this audience, nothing is guaranteed secure, right? Because even if I can secure one part of it, there are other components of the system that are vulnerable. So I think we've been the same point. We've been in this situation, right? For how many years have we been using RSA cryptography, right? We cannot prove it is secure. No one has managed to disprove it's secure, and therefore the longer we've gone on with that, the more confident we've become, rightly or wrongly.
There's actually a question over here, and then there's one more at the back.
Hey. Hello. Thank you for your presentation. It was brilliant. Anything quantum is, I don't know, I'm very amateur with it, but it's just extremely fascinating. So I really do appreciate the talk today. But more as my question is, I understand that there are two corresponding states of matter and effects happening through these quantum concepts. What is currently known about the greater effects to the atmosphere through these types of technologies, and how would that roll out on more of a commercial scale as the technology progresses?
So I think by effects on the atmosphere, you're talking about energy consumption and global warming. Yeah. So, and it is a serious issue, right? When you think about a quantum computer, as I say, they're going to be very expensive to build and very expensive to run. And one of the reasons for that, apart from anything else, is that most of the technologies that are under development require a huge amount of cooling. They need to be cooled to very close to absolute zero. So that's on minus 273 degrees below zero. It's colder than a Canberra winter morning. It's going to take a lot of power to do that cooling. And so then it comes down to, well, actually, but if we can find those right problems, and the problems where it's going to be worth running a quantum computer is when it's actually cheaper to do so on that than it is on a classical computer. And those are probably going to be big problems. So there is a very good question, right? Someone asked a killer app, right? Can we afford the killer app, right? Because if a quantum, we might get to the point where a quantum computer is only valid for these really, really massive calculations. And we might say, well, actually, given all the externalities of the power consumption and the cost of doing that, is it worth doing? So glass half full, potentially it's a way of actually trying to reduce the amount that we otherwise spend on doing lots of very expensive classical calculations, because we'll find a quantum computer that can do some of these big calculations more efficiently. Glass half empty is maybe it'll encourage us to do more big calculations and increase our global energy and water consumption.
Well, even further than that, we're reaching points outside of, Earth and things that we currently understand. Because I feel like Albert Einstein warned against it in many ways and was opposed to the whole concept.
So I'm not sure if there's a question there, or is that a comment?
Well, so what's known to further reaches of what we don't know in through this technology? Like, is there any explanation to major events occurring throughout space?
Not so. Are you saying can we use a quantum computer to predict cosmological events, or are you saying what's the impact?
Isn't there there's two simultaneous states of matter, something occurring, and that there's things that I don't know. Like I said, I'm very limited in my knowledge with it, but I feel like there's a lot known and as well as unknown.
Yeah.
What would you say you're afraid of through this development, seeing that you don't see it as so doom and gloom?
I don't see it as doom and gloom. I think ultimately, and it comes out to, I think there are things we need to do to prepare, but I think the opportunities actually, opportunities are things like more efficient battery storage, more efficient materials, things like that. There's potential opportunities for a huge amount of benefit to humanity, but we do need to start thinking and planning and getting ready for that.
Thanks.
So,
I did see one more hand just up. Oh, sorry. Yeah, there's one more question. This will be the last one.
If someone's wanting to contribute to the design of like quantum algorithms or quantum computers themselves, what's some of the prerequisite knowledge and like the entry points to like contribute to the field?
Oh, well, I mean, so important subject to study would be things like maths, physics, and actually sort of computational theory or computer science theory or computer information science. The other thing that I would encourage anyone to do if they're interested in this is not only sit there, because on the one hand, you've got to go and study all these sort of maths and work out something, but go and talk to people about their problems. What are some of the things that actually, I thought about writing a program to do this, but I realized it was going to take me 1,000,000 years for it to run and execute. Because at the end of the day, it's got to be a combination of the two. It's got to be some maths that works, but it's got to solve a valuable real world problem. I didn't talk about, I'll just maybe quickly close with this. So one of the other things that, for example, Google came up with, right, is they said there was a big headline about the fact, they found some calculation that would take 1 trillion years or whatever the stupid number was to run on the world's biggest supercomputer, and their quantum processor could run it in 90 minutes, right? Or thereabouts, right? And it sounds really impressive when you say that, right? And when I looked at that, I thought, well, it might take 1 trillion years for a classical computer to run that calculation. It'd take even longer to find anyone that cared about the answer that they were giving, because they weren't trying to solve an economically useful problem. So you've got to come at it with both ends. So on the one hand, we all know, right, there's not enough STEM being studied, and definitely we need more people doing maths and physics to understand that. But also people need to get out there, go and talk to people in the world, find what are the problems worth solving that are actually going to produce a net benefit to humanity. That's maybe the last question I was asking about.
All right. Can we once again thanks Rajiv for that great presentation?